means train free situation. Train free means when they are not in the digital structure of a window. When they are discussed at the window and the window undergoing pressure and temperature, the pressure increases the volume, temperature increases the volume. As a consequence of that, the elastic response will be different. Elastic response. So we can calculate it by a computer program using the extreme price equation, and we can redo it and generate the Moore laws. And from there we will get the RE content of the fluid. When it is red, fluid is not red. Fluid are best of things. Let me tell you. Males are very gentle guys. Fluid are best of things. Thank you.
Sir, please. We have another class, so you can discuss as well.
Sir, I'm getting. No, I can discuss with you later. Let me take care of other focus.
What this is that there was hydrotherapy altered carbon and then there was a formation of secondary calcium. So the RE, what will happen to the RE? They will remobilize. Won't they remobilize within the hydrothermal activity? They have remobilized. Could they remobilize to the other rocks also?
See, these terms like demobilization, you should not use it. You say mobilization. Because demobilization is take for an ore body already found, then undergoing immobilization during deformation and metamorphosis. You say mobilization. Yes.
And then in the if
In the
metamorphism happens, then
No, these are not metamorphosis. Thank God.
Good.
Thank God. Metamorphosis will take care of it.
So part of the question is we find the both ways to the molecular structure of it. Both ways to the total content was
Very less.
very less.
Yes,
So,
because hydrophone monolithic content is much lower volume. That is why they cannot be analyzed in a uniform manner. The volume is low, you have to take it to the ice planes. Yeah, very good.
so thank you so much for such elaborate presentation. Shall we start? Yeah. So thank you so much for now I request Professor James Chair, Dr. Naliswar Sheikh, President with a momentum, and I request our Cabinet Dr. Anuj to order a short what he will please give the momentum and short meeting.
Thank you, sir. Thank you, everyone.
Quickly moving on to the next keynote talk, it will be by Professor James. This talk will be chaired by Professor Vishnu Mishra and co-chaired by Dr. Anuj Kumar. I request, please take your respective seats. I request Dr. Anuj Kumar to come. Dr. Anuj Kumar. Anuj Kumar, sir. Dr. Anuj Kumar, please, sir. Sir, I request you to felicitate our chair and co-chair of the session. With a clap.
You can do that.
Sir, I request, Lunar also to come and consider the picture in the tower. Thank you. Over to you, sir. Thank you.
Hello. So our speaker in this session is Professor Jyotiranjan S. Rao, a prominent research associate to the University System of Tamil. He specializes in geochemistry and isotope geology, focusing on Earth's magnetic evolution, from magnetic subduction to processes, from there to sedimentary basin development, so from magnetic to sedimentary basin development. Okay. And isotopic study is one often involves studying elemental and isotopic data to understand the origin and evolution of Earth's geological reserve. He is an alumnus of IIT and here he completed PhD in 1990 and conducted technical research in Canada and USA. He has received several awards, including National Botanic Award, with 8 Dr. Bachelor's, National Research Award. Dr. Ray continued to be a key figure in Los Angeles and advanced to study past geological history, volcanic activity, and magnetic evolution. His current research project includes detailed studies of active volcanoes, magnetic fields, dynamics, and geological history of Pacific river system, such as Saraswati, which he has linked with the Harappan civilization. We are honored to have you here. Yourself.
Thank you, Professor Mishra. It looks like Alok has modified that thing. All right, so I'm really glad to be here, and I thank Alok for inviting me and the Department of Geology and Geophysics. It's the first time for me to BHU, and I'm really honored to be here in one of the oldest earth science departments in the country. And of course, I was in one of the other older ones in University of Turkey. So what I have done, because Alok told me most of you will be students and BSc and geology people. Even though per se I don't work with rare earths, I have worked extensively with carbonatites as my PhD thesis work, and I continue to do, but not much really. But I thought, why not talk about the isotopes of rare earths? So there are many isotopes of rare earth elements are used, but most prominent ones are the Samarian neodymium systematics, which you probably already know. And I have few slides just to take you through. So I have kept it general, so experts might excuse me. Even though it's general, it's a bit tricky because I'm going to talk about some extinct radionuclides. So first I'll tell you what are isotopes and why we use those isotopes, particularly the ones which I'm going to talk about, and how they are helpful in understanding the earliest differentiation process with Earth. Okay, so let's see what I have for you. And actually, usually I like interaction in between, but the format is different. So we have 1 hour. So I'll try to finish it early so that you can ask me questions if you don't follow everything. Okay. So first, this is a very common slide, but for people who are new, you have heard about the elements and their chemistry, etc. So I am going to isotopes. So this is the periodic table. You must be all familiar with. We have 92 naturally occurring elements, and most elements, except a few, have more than one isotope. So isotope means equal position in the periodic table. In other words, periodic table is designed based on increase in atomic number from hydrogen all the way to, let's say, natural occurring is uranium. So increasing one atomic number, you cover the entire periodic table. So atomic number is nothing but the number of protons in the nucleus. Now, isotope means it is the same element which has different neutron number. That means in the nucleus, you have protons and neutrons together. But if you increase the neutron numbers, it's essentially the same element. However, it's a different isotope of the same element. The chemistry of the element is essentially dependent on the valency, which is the number of electrons outside the nucleus. And number of electrons is same as the number of protons. So chemically, isotopes behave similarly, usually, except for certain processes. But they have a different nuclear property because they have different neutrons in their nucleus. So that's what they are called isotopes. Now, like periodic table, if you want to arrange the isotopes, this is how it looks like. This is chart of nucleides. So this is arranged in this way. In this axis, your proton number. In this axis, your neutron number. So proton number means the elements are arranged in this fashion. And neutron number is the same element having different neutron numbers. That means, for example, I am sorry it's not focused properly. But let's say this is oxygen. So you can see this is all oxygen isotopes. The blue ones are the stable ones. So if you put in too many neutrons in the nucleus, it becomes unstable at some point. Of course, a lot of nuclear physics goes in. I will tell about all those. So therefore, we have some isotopes. Okay. Some isotopes of particular element, they can be radioactive. That means they are unstable, so they will decay. And decay means they will emit radiation like alpha, beta, gamma, etc. And even sometimes they can break apart into the heavy isotopes. They can break into what we know known as fission. And there are isotopes which are stable. That means they don't decay or they do not actually shed any radiation. So, because of this neutron number, we have two different types of elements. That's radioactive elements and stable elements. So, in earth sciences, or even in many other sciences, isotopes are extensively used. Probably you already know. So, these are the elements which are very commonly used. And in the rare earths, there are many isotopes which are utilized nowadays, but I focus on only two, as I told you, samarium and neodymium. Samarium and neodymium. They are parent vector, I'll tell you how. Alright, so what are the use actually of these isotopes? The radioisotopes are unstable isotopes because they decay with time. So you have a function of time. Therefore, radioisotopes are very useful in dating. Okay? Because you can find the timing of events, timing of formation, etc. Same way, the product itself can also be used as a source fingerprinting. That means isotope ratio or in a different, let's say, sources and different sources will have different ratios. Therefore, you can, if a product is derived from a source, it should basically carry the signature of the source. So, radiogenic isotope, that means the product. Radioactive is actually the parent and radiogenic is the product. Those ratios can be used as source fingerprinting. Similarly, stable isotope ratios, they are abundances. When you say abundance, that means one element has, let's say, 4 isotopes. Together, they will constitute 100%. In other words, if you take, let's say, carbon, if you sample carbon, the carbon will have 2 isotopes, 12 and 13. What is 12 is called mass number. That means number of neutrons plus number of protons in their nucleus is called mass number. So isotopes, there are 2 isotopes of carbon. There is a third one, but that is radioactive. And so naturally occurring you have 12 and 13. So when I say abundance means how much they contribute to the total carbon. In other words, if you take a carbon atom, the probability of getting 12 will be the abundance of that atom, or 12 C. Similarly, 13 C. So that abundance ratio changes because of processes. Otherwise, it should not change, and because it is process dependent, most of these processes are temperature dependent. So we can understand. Sorry. So we can understand a lot of geological processes, and it is extensively used in bioclimate studies, etc., because it can give you thermometry or biothermometry. So that is the use of isotopes, and surely you must be writing your classes. And how do we measure these isotopes? We use mass spectrometry. So many institutes now has, I don't know the BHU has a mass spectrometer. Most IITs have, we have of course started this mass spectrometry. So we use the abundance of isotopes and their ratios and try to figure out either time scales or processes using isotopic ratios. So this is what I mean by decay. When a radioactive isotope decays, so the parent decays to another isotope, and in the process it generates a particle, whether it's alpha particle in this case, and a lot of energy is also radioactive energy is released. So example is given here, samarium. So samarium basically it's like this. Your nucleus is breaking into two. One is your product nucleus. So samarium 147, samarium has 5 isotopes. One of them is radioactive, and that decays to neodymium. Neodymium 143. Okay, and it produces also emits an alpha particle. So this is how it looks like, and then of course you have beta decays, electron capture. There are many types of decay processes, or modes of decay. I just gave 2 examples. Beta decay. I'm sorry. This will be strontium. So rubidium decays to strontium by a beta decay. Similarly, fluorine decays to oxygen by a beta decay. So beta is basically electron that comes out of the nucleus. So this is how unstable nuclei decay to a stable nuclei. Sometimes it can decay to another unstable, which will further decay. So, and how they are used in the thing, because there is a decay law which was given by another program study in 1930s or 1902 actually. So this is the number of atoms of the parent to start with, that is N0. N is the number of parent isotopes at a given point of time, and they are related by exponential minus laboratory decay constant. So if you look at the plot of N versus time in half-lives, half-life is the time it takes half of the initial number of atoms to decay. So if you plot number of atoms of the parent, they will decay exponentially like this. Whereas the daughter grows like this. Exponentially, of course, like this. So this is what we use for geochronology because of the time. You can measure product, you can measure number of parent, and lambda is a constant, decay constant, which is specific to that isotope, which is measured in different ways. And time is the unknown. So if you know 3 of these, you can solve it for time. And that's how we utilize. Of course, there are many ways we find time, but this is the basic equation based on which geochronology is established. So radioactive isotopes or unstable isotopes are utilized for dating purpose or finding the time of events. Okay, and that's what led to the dating of Earth or the age of the Earth by dating meteorites. People ask if you want to date the Earth, why should we go to look at the meteorites? The idea is Earth is dynamic, so we don't have the most ancient of rocks preserved. So everything is recycled. So the oldest rock is probably 3.8 billion years, whereas Earth is much older. So what do you do then? So you look at the material which made the Earth. It's like a concrete, particular carbon system, right? And it has been established by many different isotopic signatures that they were probably the parents of Earth. And that's the remains of the evolution of the Earth system are still moving around as meteorites. So you study those meteorites and you date them. And if you date them, you find this kind of age, which is the age of the Earth, which is the same as the age of the solar system. There may be slight, a few million here and there with the error, but that's the age of error. So we determine using, this is primarily determined using neural embedded method. Even summarized neural method has also been utilized to find age of error by getting measurements. And applications of isotopes in general. In fact, every day we have some other application of isotopes. In forensic science or in food agricultural science, everywhere isotope science or isotope geochemistry is extensively used to fingerprint things or to understand processes. Even for archaeology, we use carbon 14 very good for primary sciences, and particularly for archaeology. So, in fact, all archaeological survey of India dates until very recently were given by BRL's radiocarbon lab. So, yes, I mean, we use a lot of isotopes in BRL and to understand various natural processes as well as date things. Okay, now I come to the, since this conference is about rare earths, so I thought, okay, let us talk about isotopes of rare earths. So I talk about this parent vector isotope systematics, samarium and neodymium. What are their chemistry? You probably know. Samarium and neodymium are rare earths, okay, and they occur in many rock formings, silicates, phosphates, carbonates everywhere there. You just heard about they being present in carbonatites, lots of them. And phosphate, of course, in monazite, there are a lot of rare earths there. And of course, if you look at all the 14 naturally occurring rare earth elements, one of them, that plutonium, you are still talking. So that is extinct isotope, which doesn't exist as element. The others are there, 14 of them. Samarium, neodymium, they belong to the lighter side. Neodymium is the lighter element. Samarium, some people classify as middle rare earth, but neodymium is definitely light rare earth. Because they are ionic radii like this, 1.08 Armstrong for neodymium and 1.04 for samarium. So they are very close. So they can kind of almost go in the same fashion. They are thinking that we are similar. However, there is a subtle difference because of their ionic radii slightly different. They behave differently during a multi-process and external process. How neodymium is more incompatible than samarium. Okay. Yes, I mean, so therefore, as I just mentioned, in chemistry, in the crystallization process, concentration of samarium neodymium actually changes the like Bowen's reaction series. You see the later crystallizing products. Okay, we have more neodymium compared to the previously crystallizing. And I don't know whether you are a talk on use of rare earths in studying magnetic systems. I will give you some brief example before I get into the actual topic of the talk. Okay, samarium element has 5 stable isotopes, and there are 44 so this is mass number. So samarium is basically has neutron plus boson is 140. These are how we write isotopes. 144, 145, 49, 50, 52, 54. These are all stable isotopes of samarium. However, it has 2 radioisotopes or radioactive isotopes. They are extremely long lived. Samarium 147 has a half-life of 106 billion years. Okay, so you can imagine Earth is only 4.56 billion years. This is almost like 3 times the age of the Earth.